Hello everyone, my name is Chan Bolomaitay. Today I want to show you guys about my term project. I'm a part in chapter 7, transcendent function and the point 7.4 exponential chain and separable differential equations. And our content today are exponential chain, separable differential equations, unlimited population growth, radioactivity, and the last one is heat transfer, Newton law of cooling. Moving on to our first content, exponential chain. So, what is exponential chain? The exponential chain is a process where a quantity increases or decreases proportionally to its size at a given time, such as decaying radioactive material, population size, or temperature difference between hot objects and their surroundings. And the equations for differential dy over dt equal to ky and initial condition y equal to y0 when t equal to 0. And our next content is initial value problem solutions. And its equation is y equal to y0 exponential and the power of kt. And quantity changing in this way are said to undergo exponential growth if k greater than 0 and exponential decay if k smaller than 0. The number k is called the rate constant of the change. And another content is separable differential equations. As you can see here, the equation of separable differential. So to understand it well, I want to give you the example. Example 1, solve the following differential equations. So dy over dt equal to exponential and the power of x minus y. For the solutions, we have to calculate and divide the exponential into the left side and the right side. And the paper is easy to integrate it, and we can find the solution easier. And our solution is exponential and the power of y minus exponential and the power of x equal to c. And another example, dy over dt equal to 3x squared exponential and the power of negative y. And the way to find it is similar to our last example. We have to divide it into different sides and integrate it, and we got the answer exponential and the power of y minus a cubed equal to c. And our another content is unlimited population growth. And the form of unlimited population growth divided by dt equal to ky. For the examples, one model for the way disease like our when the properly treat assume. And sorry, I can just assume that the rate divide dt at which the number of infected people change is proportional to the number y. The number of the people cured is proportional to the number y that is infected with the disease. Suppose that in the course of any given year, the number of the case of a disease is reduced to 20%. If there are 10,000 cases today, how many years will take to reduce the number of 1,000? So this example, they want us to find the year that will take to reduce the number of 1,000. And for our solutions, we have to find the value of y0. When y equal to 10,000 and t equal to 0, so y0 equal to 1, equal to 10,000 according to our last slide, that is our equations. And then we find the value of k when t equal to 1 year, and the number of the case will be 80%. And we replace the number into the 80%, we can say in 8,000, 8,000, I think, and we replace the value into our the equation, then exponential and the power of k equal to 0.9, and we put the natural logarithm and find the k equal to natural logarithm is of 0.8, and it's smaller than 0. And then at any given time, y equal to 1000 exponential and the power of the natural logarithm 0.8 and t. The value of t that make y equal to 1000, we set y equation to 1000. So 1000 equal to 10,000 exponential and the power of natural logarithm 0.8 and t. So we have to find the exponential and the power of natural logarithm 0.8 and t equal to 0.1. And then we can find t equal to natural logarithm of 0.1 over natural logarithm of 0.8, and it's equal to 10.32 years. And this is our last solution for the example. And moving on to another content, radioactivity. Radioactivity occurs when unstable atoms spontaneously emit radiation, forming element with radioactive decay. The half-life of radioactive element is the time it takes to half of the nuclear in the same part to decay, not affecting the initial nuclear count. And the equations for decay of radioactive element described by y equal to y0 exponential and the power of kt. K greater than 0, and its y0 is the number of radioactive nuclei present at the time 0. The number also present at any time t will be y equal to y0 exponential and the power of kt, where and the k greater than 0. And the half-life of the radioactive element is the time required for half of the radioactive nuclei present in the same part decay. So this is the picture of nuclear. As you can see here, at the top is the nuclear envelope, and the middle is the nucleus, and the little y are nuclear pore. And the right side is the carbon 14. As you can see here, I think you can search it more detail in the Google or something. I might not explain that much about the part. So for the example of radioactivity decay, the decay of radioactive element can sometimes be used to date event from the earth part in the living organism. The ratio of radioactive carbon 14 to ordinary carbon stay fairly constant during the lifetime of the organisms, being approximately equal to the ratio of the organisms atmosphere at the times. After the organism dead, however, no new carbon is in gas, and the proportion of the carbon 14 in the organism remain decreased as a carbon-14 decay. Scientists who do the carbon-14 dating use a figure of the 5,000 and 700 years for its half-life. And this example wants us to find the age of the sample in which 10% of the radioactive nuclei originally present that have decayed. And for our solution, we know that K equal to natural logarithm of 2 over half-life, and we replace the value and the property that we have, and the value of t that make exponential and the power of negative kt equal to 0.9, and we replace decay by negative natural logarithm over 5,700 years times t equal to 0.9, and we can calculate it and find the t will be equal to 866 years. And this is our last content, heat transfer, Newton law of cooling. Newton law of cooling states that an object temperature change proportionally to a temperature difference with the surrounding medium. If half is the temperature of the object at the time t and X is constant surrounding temperature, then the differential equation is dH over dt equal to the negative k times x minus xs. And for the example of our last content, a hard-boiled egg at 98 is put in the sink of 18 water. After 5 minutes, the egg temperature is 38, assuming that the water has not warmed appreciably. And the example wants us to find the longer will take like the egg reach 20. And for our solutions, that we know that x minus x equal to x0 minus xs times exponential and the power of negative kt, and then we find the x and replace the value of the property that we have, and to find k we use information that given x equal to 38 when t equal to 5. So we replace the value in our equation. We got 38 equal to 18 plus 80 exponential and the power of negative 5k. Then we just find the exponential and the power of negative 5k equal to 1 over 4. And then we got the answer k equal to 1 over 5 natural logarithm of 4, and is equal to 0.2 and natural logarithm of 4. And it's not n. Then we the egg temperature at the time t is 8 equal to 80 plus 18 plus 80 exponential and the power of negative 0.2 natural logarithm of 4 and time t. Now to find the t when x equal to 20. So we replace the value of x into our equation. We got 20 equal to 18 plus 80 exponential and the power of negative 0.2 natural logarithm of 4 and time t. So we find the exponential and the power of negative 0.2 natural logarithm of 4 times t equal to 1 over 4t. And then we calculate it and we can find t equal to 13 minutes. And this is our last solution of the example. Hope you understand it well. And I give you another example that a surrounding medium of unknown temperature is a pan of warm water uh, 46 was put in the refrigerator. 10 minutes later, the water temperature was 39, and 10 minutes after that, it was 33. Uh, for this example, they want us to use the Newton law of the cooling to estimate how cold the refrigerator was. Right, go first. For the solution, we know that t minus ts equal to t0 minus ts and time exponential and the power of negative kt. I think it's similar to our last example, which is different. One is x and one is t. And then we replace the value and uh, we know because they gave us the two value of t. So we replace and we got the two equations. And we put the equation together and we'll got the equations and we can find t that negative ts equal to 3 and ts equal to minus 3. And this is our solutions. Finally, the end, uh, the end of my presentation, and thank you for listening my presentation. Bye bye.